A ship is a major link in the global transport system. She has to be operated so that she is dependable and profitable in service. These factors are closely linked to the proper operation of the main engine on board ship. The aim of the engineer is to operate the main engine reliably, with low fuel consumption, producing optimum power output, with low maintenance cost, and preferably no breakdowns. The factors which impact on such a successful operation are fuel quality, the correct choice and use of lubricants, and good operational practices, which include an effective condition monitoring process. In real life, the engineer has to use whatever fuel is delivered to his ship within the laid-down limits. The lubricants available to him are recommended by the engine builders or the lubricant suppliers as the most appropriate for that particular plant. So, both these items are decided for the engineer by others. The engineer's role begins with his understanding of the processes taking place inside the engine and his knowledge of all the correct operating procedures involved, including maintenance. Understanding these processes begins with a few basic facts about friction, corrosion, wear, and the heat generated by the engine. Knowing the correct operating procedures begins with knowing how to get the best fuel consumption and how to use and store the lubricants on board. The task is to combat friction, corrosion, and wear, and to deal with the generated heat. So let's look at the basics of lubrication in general, but related to the conditions existing in an imaginary main engine. Let's begin with friction. Wherever two surfaces touch and move in relation to one another, there is a force which resists this movement. This force is called friction. Brakes on cars or trains make use of this force to slow them down if they're moving, or to prevent them from moving if they're stationary. Friction occurs naturally everywhere. For instance, between furniture and floor, between piston ring and cylinder liner, even between the hull of the ship and the surrounding water. Energy must be applied to create movement between these surfaces to overcome the force of friction. Then, more energy is required to accelerate this movement. When movement occurs, the surfaces tend to grind each other down, producing wear. The energy applied to produce the movement will be transformed into heat and motion. The portion of energy used for propelling the surfaces does a job of work, but the portion which simply overcomes the force of friction is wasted energy. How great the force of friction may be between two surfaces, how much of the energy applied will turn into heat, and how much into motion depends on the pressure one surface places on the other and on the relative smoothness of the surfaces. The engineer's task in the operation of the main engine is to reduce the friction between moving parts to a minimum, to reduce the wastage of energy, while at the same time preventing the moving surfaces contacting and damaging each other, thus reducing wear. The engineer uses lubricants to perform these tasks. In general, the lubricant forms a film between the surfaces. As the shaft begins to rotate, the oil wedge lifts it off the bearing surface, attaching itself to each of the surfaces, whilst flowing steadily in the center. This is called hydrodynamic lubrication, which means full fluid film lubrication. When this condition exists, the two moving surfaces do not touch because the oil wedge separates them. If this film breaks down occasionally due to pressure between the surfaces or excessive heat or lubricant starvation, the surfaces will touch and the lubrication will not be continuous. This is called boundary lubrication. A typical situation where this arises is between a piston ring and the cylinder liner. Hydrodynamic lubrication is more effective because it reduces wear to a minimum. In the case of boundary lubrication, the surfaces may touch and wear may take place. Already, several functions for the lubricant have been identified. It must reduce friction, it must dissipate heat, and by preventing contact between the surfaces, it must reduce wear. These functions of lubrication apply across a wide variety of plant operations. To understand how all this is done by the lubricant in a main engine, we need to examine how these various problems arise there. Friction is there as a natural condition between two moving parts. Heat may be present as a result of combustion or as a result of friction. Abrasive wear may be caused by rust particles or metal particles from worn surfaces being trapped between moving surfaces. Also, catalytic fines introduced into the engine by the fuel. Catalytic fines are very fine abrasive particles which enter the fuel during the refinery processes. Adhesive wear occurs when the boundary lubrication fails to protect the surfaces and spot heat is allowed to build up so that metal-to-metal adhesion takes place, resulting in metal tear and hard particles scratching the otherwise well-machined surface. Adhesive wear is slightly special and only usually occurs in specific areas in special conditions, such as top dead center on the cylinder liner. But because it produces hard particles and uneven surfaces which help to aggravate abrasive wear, its prevention is equally important. Corrosive wear results from the presence of sulfuric acid originating from the combustion processes. Now that we know what problems need to be dealt with, we can establish the properties the lubricant must have to solve them. Marine lubricants are usually liquid or semi-liquid. They may be made of mineral oils, vegetable oils, or synthetic oils. Some additives are also present to enhance certain specific properties which are required for doing a designated lubrication job. For instance, the oil needs to be viscous enough to stick to the surfaces, forming a lubricating film between the moving parts. Why viscous? Viscosity is the liquid's resistance to flow. Water flows fast. Its viscosity is low. Syrup flows slowly. Its viscosity is high. When a liquid flows, it leaves a trail, a film behind. Water leaves a thin film. Syrup leaves a thick one. All liquids have viscosity, so an oil applied to lubricate some moving parts must have enough viscosity to form the film and flow between the surfaces as they move. In a word, it must lubricate. The viscosity of an oil is measured in a viscometer, which gives the results in centistokes at a measured temperature. This then allows for its classification by an SAE or an ISO number. SAE stands for Society of Automotive Engineers, and ISO stands for International Standards Organization. For example, an SAE 30 oil will have a viscosity at 100 degrees centigrade of between 9.5 and 11.8 centistokes. This story gets more complicated because the viscosity of a liquid changes with temperature. A slow-flowing oil at 40 degrees centigrade will become a fast-flowing one at 100 degrees centigrade. Some oils change their viscosity more, some less. So a viscosity index, or VI, is used to show how much an oil's viscosity may vary at different temperatures. A low VI number indicates a large change. A high VI number, a smaller change. A 75 VI oil will change quite a lot. A 150 VI oil, much less. It means that when using an oil for a job, its viscosity must be right throughout the temperature range of the job cycle. The first cardinal rule of good operating practices on board ship is beginning to emerge. Because of the many different lubricants available, with a whole range of viscosity and viscosity index, only the right lubricant must be used for each application. So, such a base oil is ready to perform the basic function of lubrication. This oil will be developed by the use of additives to meet a specific application. For engine application, the oil must prevent wear due to corrosion and deal with the acidic condition inside the engine produced by combustion gases. This is why an alkaline additive must be mixed into the oil to deal with the acidic condition. The oil's total base number, or TBN number, indicates the level of alkalinity present in the lubricant. A low number, such as 15, indicates low alkalinity. A higher value, such as 70, indicates a higher alkaline lubricant. When the oil gets hot inside the machine, it absorbs oxygen from the air. Oil oxidation is a problem because when oil combines with oxygen, it thickens and organic sludge and particle deposits may form in the oil. When this occurs in engines or compressors, it can cause serious malfunction. So the lubricant must resist oxidation. Antioxidant additives are mixed into the base oil, and here the oil is tested to find the optimum level of antioxidant additive required for a designed function. Water may enter the engine in various ways and may encourage rust formation on metal surfaces. This is dangerous because rust damages the machine's surfaces and breaks up into hard particles, causing abrasive wear, and where it originated, it causes corrosive wear. That is why the lubricant must prevent rust formation, and why anti-rust additives are required. The lubricant is churned inside the engine, and foam can form. Anti-foam additives lower the surface tension of the oil, bursting the bubbles, allowing the foam to break down quickly. High temperatures and pressures encourage the rupture of the lubricating film, which needs to be prevented if possible. So anti-wear and extreme pressure, EP additives, may be added to the lubricant. The oil is then subjected to an extreme pressure test. Its effectiveness is tested until destruction, until the test metal parts melt and are welded together. Finally, but not conclusively, the contaminating particles need to be transported away from moving parts, and these parts need to be kept as clean as possible. So, detergent and dispersant additives are also added, which help to clean the engine and keep the particles separate and suspended in the oil until they're removed by filtration or centrifuge. So now we are far away from a simple oil used simply to provide lubrication. Each machine will have its own specific set of operating conditions and corresponding lubrication needs. A refrigeration compressor will have completely different requirements for its lubricant from that of a high-performance marine diesel engine. The cardinal rule of successful operations, as far as lubrication is concerned, is reinforced. Only the correct lubricant must be used in each machine. This is where the lubricant grading and specification systems are helpful. The most relevant ones for a marine engineer are the SAE and ISO grades. Other specifications cover a range of performance levels, such as the API, American Petroleum Institute. Various military specifications require that the oil is subjected to a variety of clearly defined and closely controlled engine tests. Machine manufacturers will also provide a list of recommended lubricants for their products, and these must be strictly adhered to for best performance. On board ship, there are a variety of lubricants used for engines, compressors, transmission units, hydraulic units, turbines, and so on. As each machine will require a different kind of lubricant, they must not be mixed or substituted by any other lubricant than those recommended by the machine's manufacturers. Lubricants must be correctly stored in a clean environment and correctly handled if they are to perform to their specifications. If they're stored in a cold place where the oil may cool below its pour point, the oil may become solidified. If it's stored near a heat source, it may become heated near to its flash point and become an explosion hazard. Preferably, drums should not be stored on deck, as they might take in moisture, which will reduce the efficiency of the lubricant. The lubricant needs to be inspected and cleaned by filtering and centrifuge during its service life, according to manufacturers' recommendations. Finally, oil samples may be taken periodically from the lubricant in use and sent away for trend analysis to a laboratory on shore. There, the contaminant and metal particles in the oil are analyzed and quantified, and a picture built up of the state of health of the machine using that lubricant. Oil sample analysis is being dealt with in greater detail in Program 2. To conclude, good lubricant management on board ship is vital to effective ship operations. The most important steps an engineer must take in lubricant management are: bulk oil must always be bunkered into the correct tank and in the correct ascending order of TBN value. Delivery notes and oil samples must always be checked to ensure that the right oil has been delivered. Eliminate water ingress into the lube oil from piston cooling leakages, oil cooler leakages, jacket cooling water entering the crankcase, purifier seal water, and excessive water level on engine tank tops. Check pipework for leaks and failures. Check drains and filter cocks not being left open. Check tank gauge glasses not being broken, or that reading cocks are not jammed open. Send good lube oil samples for routine analysis regularly. Most losses and contamination of lube oil results from careless handling. Take great care that you handle and use lubricants correctly. Finally, the cardinal rule again. Only the right lubricant must be used for each application. View this video again and use the accompanying booklet to remind you of these very important basic factors of marine lubrication. In Program 1 of this series, the basic principles of lubrication, the functions of lubricants and their main components were discussed in general terms. From this basic look at lubricants, the most significant rule in marine lubrication has emerged. With so many different lubricants used on board ship, designed for particular applications, great care must be taken not to mix lubricants or use the wrong type for a given application. Serious damage can occur if this rule is disregarded. This program deals with specific lubrication areas in slow-speed crosshead engines and in medium-speed trunk piston engines to promote good operational practices and to help achieve the best results from the lubricants used. Good operational practices concentrate on the choice of lubricants for each application, the selection of optimum feed rate for cylinder lubrication, and the cleaning and testing of the lubricants during their operational life. The lubrication of a slow-speed crosshead engine involves three distinctly different areas. A, circulating system lubrication, which takes care of the bearings and moving parts in the crankcase. B, cylinder lubrication system, which takes care of the lubrication between the liner and the piston rings. And C, the lubrication of turbochargers, hydraulic governors, hydraulic exhaust valve actuators, and the turning gear. All of these may use different lubricants. The circulating system oil is there to lubricate the moving parts of the running gear and provide the drive for the control system. Typically, this would be an oil of viscosity grade SAE 30, having a viscosity index of between 80 and 100 and a low TBN number. The oil should resist foam formation and possess good water separation characteristics. The engine manufacturer's manual will contain recommended lubricants. Besides lubrication, the lubricant will transport contaminants and metal particles as it circulates, which then need to be removed. This is best achieved in a centrifugal separator, working in bypass, drawing oil from the oil drain tank and returning it there after cleaning. The application of inline filters also helps to remove some of the contaminants. The ingress of water into the system is always a danger, and frequent checks should be carried out on the system oil to ensure an early detection and removal of water. This is most important, as the presence of water increases the risk of corrosion as well as microbial contamination of the oil. The water must be kept out or removed totally as quickly as possible from any system oil. Again, systematic centrifugal cleaning will lower these risks. Typical sources of contamination may be leakage from the cooling system and from the centrifuge sealing water if not operated correctly. The cylinder lubricating system uses a different type of lubricant, as the job it is required to perform differs from that of the system oil. The cylinder lubricant must be of a higher viscosity so that it can form a good lubricating film between the liner and the piston rings. It must also withstand the heat variations in the combustion area and must deal with the combustion products. Under normal running conditions, an alkaline cylinder lubricating oil of SAE 50 viscosity is used. The alkalinity or TBN value of the oil is related to the sulfur content of the fuel used. Typical values may be for sulfur content of 0.5 to 1% between 20 to 25 TBN. For higher sulfur content over 2%, the TBN number may be 70 or higher. Once the correct cylinder oil is chosen, the correct feed rate must be established in accordance with the engine builder's recommendations. The feed rate has a critical effect on good engine operation, apart from the question of oil consumption. With too low a feed rate, the danger of the oil film breaking down, causing undue wear, is much increased. The correct feed rate will allow the formation of the lubricating film between the liner and the rings, and will reduce the effect of its breakdown at piston reversal points. The use of heavy fuel oil with high sulfur content is making the job of the cylinder lubricant very difficult. Even high alkalinity oils cannot hope to neutralize all the sulfuric acids which are produced during combustion. The cooling system must be operated so that the cylinder liner temperature is not dropped below the temperature at which the sulfuric acid may condense out on it. Acid condensation depends on the engine combustion pressure, the liner temperature, the concentration of the sulfur oxides, and the humidity of the intake air. So the engineer must ensure that the moisture content of the intake air is meticulously controlled, and that the temperature of the cylinder liner is kept high enough to prevent acid condensation. The way an engine has been run in after commissioning or an overhaul is critical to establishing good cylinder lubrication. A good run-in procedure will create a good wear-in of the cylinder liner and piston rings. A good seal is obtained between them where a thin oil film provides reliable and effective lubrication. To achieve this running-in performance, a running-in cylinder oil may be used. The period of running in should be decided upon in accordance with the engine manufacturer's recommendation. Even if only new rings have been fitted, the running in procedures should be as near as possible to that recommended for new engines. During the running in period of a new engine, the feed rate should be high. After running in, the feed rate is gradually adjusted until the recommended feed rate is reached. The use of the correct lubricant and the correct feed rate for the engine load will help to achieve the best results from a cylinder lubricant. The lubrication of ancillary equipment of the main engine will be discussed in Program 3. Due to vital design differences, in the case of medium-speed diesel engines, the cylinders are open to the crankcase. This means that the crankcase oil can be contaminated by corrosive combustion products. The chosen system oil must deal with these contaminants as it lubricates the system. The lubricant must also maintain effective lubrication under high mechanical and thermal loads, and must transport solids from the cylinder to the cleaning devices, such as filters and centrifuges. It must withstand heat as it fights corrosion and wear. In doing this, it must resist oxidation and thermal breakdown, and must keep the engine clean. Some medium-speed engines, in addition to high load factors, introduce new problem areas for the lubricant to deal with, such as piston undercrown deposits, ring zone fouling, and cylinder bore polishing. So the lubricant must also have increased dispersancy detergency, higher oxidation, and thermal stability. It must also have higher load carrying capacity to avoid scuffing problems of cams and rollers. The aim is to maintain effective lubrication at all times throughout the machinery. Inside the cylinder, the thermal and mechanical stresses on the oil film peak due to combustion while the piston speed is 0. The oil film can break down easily, and the best the engineer can hope for is sufficiently effective boundary lubrication at this point. In medium-speed engines, the circulating system oil is also providing cylinder lubrication and piston cooling, and the breakdown of the lubricating film between the liner and the piston rings tends to cause blow-by, which results in further contamination, including unburned fuel. Unburned fuel contamination tends to reduce viscosity, leading to less effective lubrication. The main source of fuel contamination is a leaking fuel injector. A typical lubricant which will successfully lubricate the entire engine is an SAE40. The oil will generally be designed with additional alkalinity, detergency, dispersancy, with antioxidant and EP additives. In all cases, the engine manufacturer's recommendations should be strictly adhered to. Some medium-speed engine designs use a separate cylinder lubricant, but in almost all cases, the system oil is used for cylinder lubrication. Lubricant care is a critical factor in good machine operation. The conditions of storage on board, prevention of contamination by water and hard particles during storage, the cleanliness of the machines when charging them with lubricants, and the continuous filtering and cleaning of the lubricants during use are equally important phases of looking after them. There are many filter types used on board ships, and their periodic cleaning and monitoring according to manufacturers' recommendations is essential. Medium-speed installations use back-flushing or self-cleaning filters. Pressure differential between inlet and outlet triggers off back-flushing. If difficulties arise with this type of filter, for instance, frequent back-flushing, the filter elements should be dipped into chemical cleaners which are capable of dissolving and removing hard calcium compound deposits. Or an ultrasonic bath may be used for cleaning them. Filtering the lubricants will only remove some of the contaminants, usually the larger hard particles. The lubricants need further cleaning, and the use of purifiers for this work is common practice. These will remove particles as small as 0.5 microns and remove most of the water content. Increased use of lubricant condition monitoring and wear metal particle analysis greatly reduces operating costs, as the resultant trend analysis usually highlights impending problem areas before breakdown occurs. The savings come not just from avoiding unexpected breakdowns and their consequential costs, but from being able to eliminate problem areas before they contaminate the lubricant, forcing its untimely replacement. The combination of wear and contaminant elements usually points to specific developing problems from which practical recommendations can be built up, reducing the need to open up the machinery for inspection or discarding lubricants before their time. The main items which are checked during analysis are flash point, viscosity, water content, alkalinity, and metal wear particles. The resultant values are then compared with those of the new oil to detect major changes. For the oil analysis to be effective, the job must be done using good representative samples taken preferably after the pump, strainer, cooler chain, before the oil re-enters the engine. In any case, the samples for trend analysis should always be taken from the same point in the system. The method of taking the sample, as well as the utensils used, must be such that contamination of the sample is avoided. In the laboratory, the lubricants will be examined for the presence of combustion contaminants, as well as for metal debris against established control values. Increasing trends and their combinations will allow the required remedial measures to be formulated. Modern lubricating oils, when carefully monitored and maintained in good condition by the engineer, can have an almost infinite life. Even if this optimum is not always achieved, extended oil change intervals will reduce used oil disposal problems with significant cost and environmental benefits. In Program 1 of this series, the basic principles of lubrication and the functions of lubricants and their main components were discussed in general terms. Program 2 dealt with the lubrication of the main propulsion engines of the slow-speed Crosshead type and the medium-speed trunk piston type. In this program, the lubrication of the ancillary equipment on board ship is discussed in detail. The lubrication of ancillary equipment on board ship is just as vital as that of the main engine, as some of the ship's control systems, such as the steering gear, rely on hydraulic pumps for their efficient service. Refrigeration plants, deck machinery, gear transmissions, cranes and ropes all have their own specific needs as far as lubrication is concerned. The cardinal rule that was established in Program 1 about lubrication is that each specific lubrication job requires its own lubricant, specially designed for that job. Lubricants must not be mixed or the wrong lubricant used, because disaster is likely to follow in either case. On today's vessels, most tail shaft bearings are oil lubricated. The stern tube is filled with oil and a static pressure head is applied via a header tank. The height of the header tank is calculated to ensure that the pressure head of the lubricating oil will always be higher than that of the seawater outside. Failure of the outer seals will thus always result in loss of oil rather than seawater ingress. As far as the lubricant is concerned, only oils which are fully approved by the manufacturer should be used, to avoid using products which may be incompatible with the materials used for the shaft seals. The engineer should pay regular attention to the level of the stern tube oil header tank to monitor any leakage from the stern tube outer seals. In the case of heavy leakage, the engineer must decide the point at which he believes an emergency situation exists. At this point, he should introduce any heavy oil available to him on board the vessel, for example, an SAE 50 cylinder oil. This will slow down the rate of leakage and allow him to reach port where repairs may be effected. In the event of him calling at a port prior to the repair port, he should ask his oil supplier to deliver a very heavy stern tube oil. Regular samples should be taken from the stern tube oil from the sampling cock, having first allowed a reasonable quantity to be drained off to ensure a good representative sample. The oil should be tested for water content and for wear metals content, since all of the classification societies now use wear metals trend analysis to assess the condition of the tail shaft bearing. The steering gear on an ocean-going vessel gives a classic example of the simple hydraulic system. If the vessel is fitted with a rotary vane system, the stator is fixed to the ship's structure and the rotor to the rudder. In the annular space between the rotor and the stator, fixed vanes are fitted, secured equidistantly around the outside of the rotor. They form two alternative pressure chambers, each connected hydraulically by a manifold. Oil is then delivered under pressure to one chamber or another, turning the rudder in the desired direction. The hydraulic fluid in a steering gear system is not subjected to undue stress. Hence, a good quality hydraulic oil of the correct viscosity will suffice. It is important that the viscosity requirements of the hydraulic pump manufacturer are observed, and that the oil is kept clean and free from moisture. So long as the system is leak-free, there will be little make-up required, but it's essential that frequent and regular checks are made on the reservoir level indicator. Equally important to the steering gear is its control system, usually known as the steering telemotor. This is also a simple hydraulic system, where the hydraulic pressure is applied by the helmsman turning the ship's wheel, or, more commonly in modern ships, by an electrically driven motor controlled by the automatic pilot. The hydraulic fluid is transmitted through a long length of small bore piping. Hence, fluid friction becomes an important factor. Since instant response is required, it's necessary to use an hydraulic oil with the lowest practical viscosity and with the highest practical viscosity index. This can be satisfied with an ISO 15 oil having a VI of 150. By virtue of its high VI, the oil will have a low pour point of around minus 50 degrees centigrade. Also an important factor. The steering flat holds another lubrication area, and that is the lubrication of the rudder stock bearings, particularly the carrier bearing. Unfortunately, conditions in the rudder carrier bearing will never permit anything other than boundary lubrication, and the lubricant used is normally a grease containing load-carrying additives. The rudder stock bearings carry little load, but they do need lubrication to protect against wear from vibration. The upper and lower bearings are both lubricated from the carrier bearing lubrication system. There are a number of different types of gearboxes on board ship, ranging from the large gearing required for main propulsion by medium-speed engines, the open gears on the windlass, to the very heavily loaded gears on the purifier drives. Each requires a different lubricant. Main propulsion gears are not heavily loaded, and for this reason, in most cases, the main engine oil can be used in the gearbox. On very heavily loaded gears, it is not possible to maintain hydrodynamic lubrication between the gear teeth, and metal-to-metal contact can occur. To overcome scuffing of gear teeth under such conditions, the gear oil is fortified with additives, usually a combination of sulfur and phosphorus. These additives react with the tooth metal under the high temperatures generated by metal-to-metal contact to form a protective metallic film. Such oils are classified as EP, extreme pressure oils. When high tooth loading is combined with very high temperatures, then standard EP oils may not be sufficient. For such cases, it may be necessary to use synthetic-based oils, and a typical requirement arises for the lubrication of certain purifier gearboxes. Special compressor oils have been developed for use in certain designs of air compressors. These oils have to lubricate compressor pistons or vanes where high temperature and high pressure exists, and where air humidity can condense into water droplets. These oils must have a good anti-oxidation stability. The oils must also have a good air separation ability and an anti-foam additive. Extreme cleanliness must be exercised when charging lubricants into compressors. Because there is a tendency for carbon buildup on valves and valve seats, often synthetic oils are used as base oils for compressor lubrication. Deck machinery is exposed to a wide range of climatic conditions, and the lubricants used must be able to operate under great temperature variations. This is particularly true for the hydraulic oils used in deck winches and cranes. The hydraulic oil must have very low pour point to allow the winches to start turning under Arctic conditions, and it must have sufficient viscosity for satisfactory lubrication under tropical conditions. This is achieved by providing an hydraulic oil which contains viscosity index improvers to give a VI of 150 minimum. At sea, the deck machinery is exposed to sea spray, so open gears and wire ropes need to have good protection against corrosion. For this purpose, special protective greases have been developed, and it is for the engineer to ensure that they are adequately applied. In all modern refrigeration systems, the refrigerant is a Freon-type product, often R22, and the lubricant has to mix with the refrigerant in the compressor. Although oil separators are fitted on the outlet side of the compressor, there is always a certain amount of lubricating oil carried over with the gas into the evaporator coils, and then back to the compressor. For this reason, refrigerator oils have several critical requirements. They must be moisture-free, they must have low pour point, and they must be compatible with the refrigerant. The latter point is indicated by the critical solution temperature of the oil. This is the lowest temperature at which the oil is fully miscible with the refrigerant. If the temperature in the evaporator drops below this temperature, the oil may drop out of solution and the evaporator will become oil-logged and the plant will fail. Synthetic oils have lower critical solution temperatures than mineral oils do, and they are more often specified for modern, highly rated installations. Because refrigeration oils must be moisture-free as well, it's most important that they're ordered in small containers and that the containers are completely emptied on each occasion. Partly used containers will allow the oil to absorb moisture from the atmosphere. We have established already the cardinal rule of lubrication on board ship. Only the correct lubricant must be used in each machine. This rule is vitally important in the case of refrigeration plants. Lifeboats and emergency standby systems, which are usually driven by diesel engines, are subjected to intermittent use. These machines are relied upon to work perfectly when necessary, whilst idle most of the time. The lubricants used in them must be capable of protecting the equipment against corrosion, while at the same time providing lubrication instantly. For this reason, they invariably use a multigrade oil. Not checking that enough lubricant of the right quality is always available in the machinery under your care, or using the wrong lubricant in a machine, will result in catastrophic breakdown of bearings, gears, pistons, or liners. These examples will remind you of the importance of choosing the right lubricants, storing and using them correctly, and monitoring their condition as well as their available quantities regularly. In short, ensuring that the machinery in your care is well lubricated at all times.